Well, you made it to the second video on sequences. Congratulations. All right, you're making good progress, and I can see a good pattern in the way that you're actually starting to study for math. All right, and sequences, of course, are all about patterns. All right, so we'll go forward with the idea that you already know the difference between an explicit and a recursive sequence, and we're going to introduce a few more terms here to see how sequences can be applied. So, as we go through, we got a few examples, and I'm going to introduce a few terms here. First of all, if the terms of a sequence approach some sort of a unique number, we say the sequence converges. You may recognize kind of this terminology about approaching a number. You may think, oh yeah, that's kind of like the limit that we learned earlier this year. Otherwise, we say the sequence diverges. So if we go to a certain number, the sequence converges, otherwise the sequence diverges. So let's take a look at a couple of examples here. We want to determine whether or not the sequences given are convergent or divergent. So the first sequence right here is an explicit formula. We got a sub n equals negative 2n plus 5. Let's write out a couple of terms here. If n is equal to 1, I plug in 1 for n, and I get the first term is 3. When I plug in 2 for n, I get 1, and then I get negative 1. You might notice that I'm just subtracting 2 each time. I wonder what that has to do with the slope of this. But it seems like these terms are not approaching a finite number, so we say the sequence is divergent. A situation where we might actually approach some sort of a finite number is the sequence in B. If I write out some terms here, right, we've got a sub 1 is equal to 1 over 4 when I plug in 1, and I get 0.25. A sub 2, when I plug that in, I get a decimal here that I've got as 0.286, and I've worked all these out right here. And look, the main thing is we're trying to see what this function approaches or what the sequence approaches. And if you look, it looks like we're approaching some number that's close to a third. And in fact, there's a reason for that. If you remember our rational functions, all right, we've got a degree n to the first on the top and a 3 n to the first on the bottom. So as our numbers go higher and higher, as n gets larger and larger, it looks like we approach the number 1/3. Okay, sorry about that break there. I had to make a quick correction on example C here. So a sub 1 is 24. And a sub n is equal to 1/2 times a sub n minus 1. And this is what we call a recursive sequence right here, where we're defining our previous terms, our next terms in terms of our previous terms. All right, so what do? A sub 1 is equal to 24, and this tells us that our next term, like a sub 2, is 1/2 of the previous term. So a sub 2 is 1/2 of 24, which is 12. And then we divide by 2 to get the next term, which is 6. And then we go down to 3, and then to 1.5. And as you keep on going, you'll notice that the terms are getting closer and closer to 0. So we say that this sequence converges. All we're doing is we keep on dividing by 1/2 and by 1/2 and by 1/2 and by 1/2. And eventually we're going to get down to a number that approaches 0. All right, some new terms here. A series is what we're going to call the sum of all of our terms in a sequence. And we can, again, have either a finite or an infinite series. And the sum of the first n terms of a series is what we're going to call the nth partial sum. So like the fifth partial sum is the sum of the first 5 terms of a series. So find the fifth partial sum of a sub n equal to 7 over 10 to the n. Right? So if we write out our first 5 terms, this is an explicit formula. So I can plug in 1 for n, and I get 7 over 10. And then I plug in 2 for n to get the second term. I get 7 over 10 squared, or 0.07. And notice every time that I do another term, I add another 0. So a sub 3 is 0.007, a sub 4 0.0007, a sub 5 0.000007. Right? So notice the sequence itself is going to converge. These terms are getting closer and closer to 0. But that's not what we want here. We want to actually find the fifth partial sum, which means what happens when we add up the first 5 terms. In this case, we got a 0.7 plus 0.07 and so on, and this becomes 0.77777. Interesting. And has everybody ever seen those like repeated decimals? I wonder if that's connected somehow with what's going on here. Maybe. We'll study that later. All right. Another new notation that you'll learn for this summation is what we call sigma notation or summation notation, right? And sigma notation uses this big capital letter sigma, a Greek letter here. So some important parts of this, all right? We're going to say k equals to 1. K is what's called our index of summations, or index number. And 1 is what we call the lower bound of our summation. And what this stands for is we want to add up all of the numbers a sub 1 plus a sub 2 plus a sub 3 all the way up till a sub n, which is our top number right here. It's not necessarily going to be an n. It could be like a 10, which means we need to add up all the numbers when we plug in the numbers 1 through 10. And we're going to use integers, so 1, 2, 3, all the way up until n. N is what's called the upper bound, and 1 is what's called the lower bound. So let's see an example here. So what we've got is we've got the sum, that's how we pronounce this sigma right here, of k equals 1 to 3 of k cubed plus 2. Well, what does that mean? It means I start at k is equal to 1, and I plug 1 in for k. So the first time I plug in, I get 1 cubed plus 2. When I plug in k is equal to 2, that's the next integer, I get 2 cubed plus 2. And when I plug in 3, I get 3 cubed plus 2. So all we're doing is we're adding up the first 3 terms of k cubed plus 2. Right? When I work that out, I get 3 plus 10 plus 29, which is equal to 42. Right? So the summation means add up terms 1 plus term 2 plus term 3. Here in B, we've got starting at k is equal to 2. You don't have to start at 1. You got to pay attention to where your starting point is. So it's saying plug in 2 first, and then plug in all the integers all the way up to 6. So when I add this up, I get 1/2 plus 1/3 plus 1/4 plus 1/5 plus 1/6, and the top upper limit up here tells me to stop at 6. So I add those up on my calculator, and I got 1.45. Ooh, wait a second here. The sum from k equals 1 to infinity, all right, of 1/10 to the k. All right, so when I start to write out some of these terms here, right, this is an infinite series. And when I write out some terms, I get 1/10 plus 1 over 10 squared plus 1 over 10 cubed plus 1 over 10 to the 4th. In decimal notation, that's 0.1 plus 0.01 plus 0.001 plus 0.0001. And you notice that's a repeating decimal. Does that look familiar at all? Well, it should, because this is equal to 1/9, all right? It's 1 repeating is 1/9. So this summation right here, this infinite notation, right, eventually became this repeating decimal, which was 1/9. More on that in some future videos. All right, now let's go the other way. Can we write a sum in sigma notation? So I've got 1 over 25 plus 1 over 30 plus 1 over 35 plus 1 over 40 plus 1 over 45 plus 1 over 50. And I want to start with my lower bound k equal to 5. So first of all, let's see if we can try to find a formula. Well, it looks like what we're doing is if we start at 5, right, the first term is 1 over 5 times 5. The next term would be 1 over 5 times 6, and then 1 over 5 times 7. That's what 35 is. And it looks like we got a nice formula here. A sub k is 1 over 5k. So now we determine our lower and upper bounds. Well, it told us where to start. K is equal to 5. And where do we end? Well, when we get 1 over 50. And we get 1 over 50 when k is equal to 10. So putting it all together, all right, we would say the sum from k equals 5 to 10, so lower is 5, upper is 10, of the formula 1 over 5k. And if you notice, when I plug in k is equal to 5 to start, and then 6, and then 7, and then 8, and then 9, all the integers up to 10, all right, then I get it to match the formula that I had at the very top. All right, so in summary, sequences can either be convergent or divergent, depending on what terms they eventually level off to. And sigma notation is going to be a convenient way of writing our series or the sums of terms of a sequence, right? An nth partial sum is the sum of the first n terms of a sequence that has a special name there. Thanks for listening. We'll see you in the next video.